Well, it's a pleasure to welcome Andy back to IAS. He will tell us progress in flat space about progress in flat space holography, and I think there will be questions throughout and afterwards.
Okay. Does it look okay? Everybody can see the screen.
Okay, perfect.
Okay, great. So I'm going to talk about progress in flat space holography, and I love giving seminars at your place. I wish I was down there. It's always so much fun. The coffee's good. I love walking to the oak tree, even though it's been chopped down now. But we'll have to make up for it later. Okay, so I'll start out with some motivation and review. And anybody who's heard me give a talk recently, this will be, you've heard this part before. And then I'm going to talk about some recent papers, one with Monica Pate, Anna Reclario, and Alice Yuan on celestial OPEs of gravitons and gluons. Another one with Mina Himwich, Shruti Narayanan, Nisarga Paul, and Monica. And then two papers that are in progress or soon to appear. The first one with Nima and Monica and Anna is in draft mode. And then the second two with Alex Tonsov, Melton Walker, and Anna on doing a conformal block decomposition of the scattering amplitudes. It's pretty far along, but still have some things to figure out. And similarly with the one with Alfredo Guevara, Mina, and Monica. So let me just start with the basic idea. So the basic idea is that we might hope to understand scattering in quantum gravity in asymptotically flat, asymptotically Minkowskian spacetimes in terms of what we call a celestial conformal field theory that lives on the celestial sphere, which is the thing we see when we look up at the sky. It's the sphere at null infinity. And the basic idea is that correlation, that the S matrix, where the incoming states are labeled by their incoming angle along with other parameters like energy and charge, are each represented as insertions in on a sphere, a sort of correlation function in a sphere. And what's nice about this is that the Lorentz group, which is SL2C, acts like the conformal group on this two-dimensional celestial sphere. And moreover, it's been understood that actually that global conformal group, as often happens in systems that have a global conformal SL2C symmetry, it gets enhanced to the full infinite dimensional group generated by two Verisaros. But that's far from the end of the story, because as we've learned in the last 5 or 10 years by careful studies of soft theorems and so on, this collection, either whether we think of it as the bulk S matrix or a correlator on the celestial sphere, has many more symmetries other than the familiar ones in two-dimensional conformal field theory. In particular, a simple symmetry like just space-time translation acts in a very exotic way, mapping an operator of conformal dimension delta to an operator with conformal dimension delta plus 1. And how this is possible, how you can have a structure that that incorporates all these symmetries at once. It seems like a greatly over-constrained problem, but we know it must have a solution. It's very hard to see how this all works out, and that's what we are trying to understand. Now, the very first step in finding a holographic duality is to understand the symmetries that both sides obey. Indeed, in Juan's discovery of the AdS-CFT correspondence, I think he could correct me if I'm wrong, but I think the first thing was the big key was the discovery that the isometries of anti-de Sitter space mapped exactly into the conformal groups of the field theories that could live on the boundary. So that is certainly a step that we'd like to start with in understanding a holographic dual for flat space. And this idea occurred to de Boer and Solodukin in the early 2000s, and they thought of it in the following way. Let's take flat space and slice it up in this hyperbolic slicing and view flat four-dimensional Minkowski space as kind of a non-compact compactification over anti-de Sitter space. So here we have Euclidean anti-de Sitter slicings, and here we have three-dimensional de Sitter slicings, all of which have the same isometry groups. And then viewed in that way, they conjectured, since Euclidean anti-de Sitter space has a boundary, which is nothing but the celestial sphere, that there should be an infinite dimensional conformal group that acts there. Now, there was a confusing point at that time, which is they seemed to think that there were going to be, by the way, you can see the little hand, can't you? Yeah. There seemed to be two infinite dimensional conformal groups, one from here and the future, one from the past celestial sphere and one from the future celestial sphere. But one thing that we've understood from the study of soft theorems is that these conformal groups, if you ask what is the symmetry of the S matrix, these two conformal groups are locked together. That's what the subleading soft graviton theorem tells us. And so we have one of the nicest objects that we could have. So we have only one copy of the conformal group that's a symmetry. And so we have one of the nicest objects that we could have, which is a conformal group acting on a single copy of the celestial sphere. But there are many things about this that we still don't understand. And we'll be talking about this, but let me say why it's interesting. So I don't think anybody believes that holography, the holographic nature of quantum gravity, is something which is restricted to anti-de Sitter space. And we'd like to find other generalizations, and certainly flat space would be an important one. The other thing is that the many symmetries in trying to understand black hole information, even energy conservation, as has long been understood, forces correlations between the outgoing quanta and Hawking quanta and the quantum state of the black hole. And now all of a sudden we find that there are actually infinitely many symmetries at play. And we'd like to understand how they affect the problem of black hole information. Also related is many people from different points of view, I'll have a few more words to say about this later, have been trying to understand what the most general form of the 4-point graviton scattering is, which is consistent with all the good principles that we'd like it to have. And here we have more of them to add to the already rather long list that people are discussing. Also, we'll see the study connects with many recent developments in mathematical physics. And finally, I just want to emphasize that this discussion has been primarily bottom up. We're discussing properties of the real world in a new way. And indeed, this new way of looking at things has led to some interesting ideas for novel experiments, which will predict interesting properties, including not just the standard memory effect, which will be measured at LIGO, but the spin memory effect, which they're hoping to measure, color memory, which they're hoping to measure at the already funded electron ion collider, and so on. So this is all very directly related to everything I'm going to say is directly relevant to the real world and has been mostly bottom up. So in this holographic duality that I'm discussing, it's rather different than the way things have proceeded in string theory. So far, the left-hand side, namely the bulk S matrix, has largely been defining the right-hand side, the correlation function on the sphere. And one could imagine on some other planet where, just to try to explain this, one could imagine on another planet where it had been Brown and Hanot, their analysis had been understood, but string theory was not well understood. And the AdS CFT correspondence was understood by starting with Brown-Hanot and conjecturing about what kind of, you might have guessed that there was a conformal field theory on the boundary, and you could have analyzed its properties and guessed about what sort of bulk quantum theory of gravity would satisfy that, and conjectured an AdS CFT correspondence, and probably learned quite a bit about it. There's no substitute for having a complete microscopic definition, but one could have understood quite a lot that way. And that's the route that we have mostly been following in this program. Now, a top-down approach where we actually construct the dual CFT somehow from string theory. Indeed, the string world sheet is a two-dimensional CFT from whose correlation functions we construct a four-dimensional S matrix. There seems to be some kind of connection here. It's possible that we could find some top-down model that would give us an intrinsic construction of a celestial conformal field theory. And this would be a major breakthrough. This would, I'm not claiming we've done anything like that. This would be a major breakthrough. It would be extremely interesting. But even along the way, as you'll see, just studying the low energy symmetries of quantum gravity is forcing us into a picture which looks a lot like the one that we have developed from string theory. So as I said, flat space holography and AdS3 holography, they have similarities, but they're different. One of the most outstanding differences is that in AdS holography, the states of the dual are the same things as the states of the bulk. That's not going to be true in flat space holography because the dual theory is Euclidean. Also, these celestial conformal field theories, they're not your usual garden variety conformal field theories. They have operators with negative dimension and other kinds of exotic properties that we need to, that we'd like to understand. So here's a sort of list of what's similar and what's different. They both have two Virasoro algebras. Celestial conformal field theories also have current algebras whenever you have a gauge theory in the bulk. In usual conformal field theory, one talks about OPE singularities. In celestial conformal field theory and scattering theory, you talk about collinear singularities, and these are dual to OPE singularities. The kinds of representations that we deal with here are not the usual discrete highest weight representations. One considers more generally continuous complex highest weight representations, but these are representations that have come up a lot in various studies of the bootstrap and so on. There's the locality properties are different. A lot of things we don't understand. There's space-time crossing. There's supposed 4D and 2D crossing in a celestial conformal field theory. We don't know what the 4D crossing would be here. The biggest thing that's new, though, is this existence of infinitely many new symmetries, in addition to the already infinite number of symmetries that are present in a usual conformal field theory. And we would have thought that was impossible, but we know that we can construct a collection of such objects just by transforming the usual bulk S matrix. Okay, so there's a very rich structure here. There's a lot of work in different directions. I don't think there's a coherent overarching picture about how we're supposed to think about a celestial conformal field theory, but there's a lot of really fascinating tidbits that are coming out, and I'm just going to present some of those and try to excite your interest. And of course,
Andy, could I ask a question?
Yeah.
So are these CCFTs only defined on spheres, or can they be defined on higher genus surfaces? And related to that, do they have modular invariance properties in the spectrum?
Yeah. Is that Greg?
That's me, yeah.
Yeah. So I think, and this is a project which we haven't made a lot of progress on, but I do believe that the torus appears. And the way that the torus appears is that, I mean, it's a question I would love to answer. We're at a more preliminary stage than that, but the way that the torus appears is if you study the symmetrics, which are in fact boost eigenstates, the ones that where you have a pair of black holes leashed on a string that are accelerated off to a null infinity. And these have played an important role in understanding black hole entropy and in ER equals EPR. They're very interesting exact solutions of Einstein, which have been known for almost a century, but we keep understanding new things about them. And what happens is they go out to the celestial sphere. They make it to null infinity because they're uniformly accelerated. And then they puncture null infinity, and they're correlated. The quantum states of the black hole are correlated. We can see that directly from computing the action of the instanton that creates these things. And that is like taking a conformal field theory on a sphere, inserting a complete set of operators and summing over them, which we know from sewing turns the sphere into a torus. We can also see this same torus in another way, which is if we look at the Euclidean section, there's a U1 cross U1, and this torus is the orbits of the U1 cross U1. And in some sense, it looks as if the celestial conformal field theory lives on that torus, and there's a relationship between the partition function of the celestial conformal field theory and the action of the Euclideanized symmetric. And moreover, there would be some sort of modular property, not modular invariance, but a modular property where you maybe change the string tension that the black holes are leashed on and the temperature. You exchange them, you exchange various potentials. So it would relate one partition function to a different one, as often as typically would happen in conformal field theory. But I have just gone way, 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 way beyond what I understand in a concrete way. But it is a hope that that there'll be some sort of modular property that we can study. Okay, so now I'm going to go back to talking about what a celestial amplitude is. For massless particles, it's a very simple thing. You just take the momentum space amplitude and you reparameterize the momenta in terms of the incoming or outgoing angle, which I'll denote by Z, on the celestial sphere, and the energy omega. And then you do a melon transform with respect to the energy, and the coefficient of that melon transform becomes, we have to worry about the spin factors, becomes the conformal weight. And then this thing transforms by construction, this melon transform of an S matrix of massless particles transforms covariantly in the standard way as a correlation function in a conformal field theory. And then Pistersky and Shao, in an important paper, showed that if you allow the conformal weights to take these values, which lie on the continuous unitary principal series, that the resulting wave functions form a complete basis for normalizable wave packets. That is an important result. We have to take it with a word, I'm going to say a word of caution, which is that that particular space of normalizable wave packets is not closed under translations. So if we just do a time translation, we multiply the wave function in momentum space by omega. So something which is a normalizable wave function, if we act on it enough times with the Hamiltonian, might not be normalizable anymore. And so for the purpose of understanding all the symmetries that we want to understand, we will at times be considering more general values of H and H bar. And indeed, the soft currents that are responsible to the soft theorems are not, don't lie on this unitary principal series. Now, there's also a beautiful story for massive particles, which instead of the melon transform, one does a convolution with a bulk to boundary AdS propagator, and you again get an object that transforms like a conformal field theory correlator. There have been a lot of computations of various scattering amplitudes in the conformal basis. And one thing I want to emphasize here, to borrow Nima's phrase, is that good ultraviolet behavior is baked into the whole discussion from the beginning. So actually, even at tree level, you can have an ultraviolet divergence that prevents you from constructing the melon amplitude, because you have to integrate over all energies, and those integrals can diverge. So for example, for Einstein gravity, it makes no sense because the integrals just diverge, at least if you're on the unitary principal series. Even for Yang-Mills theory, it's only marginally convergent, and you have to regulate it, and you have to understand what you mean by that regulator. And I think the best way to think about the Yang-Mills theory celestial amplitudes is to think of them as the ones that you compute in string theory and then taking a certain limit. Okay, so we are only in this story really allowed to discuss things with good ultraviolet behavior. And really, it should be very good ultraviolet behavior if we want to consider arbitrary values of the conformal weight, and that really means gravity, as we'll get into a little bit more later. Now, one thing that's important about this, this whole story started, I guess, with a study of the soft theorems. And soft theorems have to do with things, behavior of gauge and photons, gravitons, gluons, et cetera, at very low energies. But we've just announced that we're not going to talk about energies anymore. We're not going to divide things into low energy and high energy. We're going to do melon transforms, and we're going to talk about things that have high boost weight and low boost weight. And so it turns out that, and this is kind of a theme, again, there's a parallel theorem in melon space to the soft theorem, which talks about the behavior of, say, gauge bosons, not as they become energetically soft, but as they become conformally soft. That is, as their conformal weights approach those of a conformal current. And it's interesting that this theorem can be proven even though this object is not restricted to low energies. And the physical picture is rather different. Usually you would say that the soft theorem holds because we have some big, flabby, soft photon, graviton coming in. It can't see the details of what's going on. Here, you can't really think of it that way because these conformally soft particles involve arbitrarily high energies. Now, that had to do with the analog of the soft photon, soft gluon theorem, but for the soft graviton theorem, it's more subtle. It involves a limit in which you take the conformal weights, so it has to have h minus h bar equals 2, and the soft graviton, the conformally soft graviton, involves something of conformal weight 1, total conformal weight 1. So this has total conformal weight 1. And the soft graviton theorem implies, surprisingly, that this thing, something constructed from this operator, behaves holomorphically in correlation functions. And that's possible because when you act on any operator, the corresponding word identity, it has a 1 over z minus w, a pole like you would expect in a soft theorem, but it transforms any operator into another operator whose conformal weight is shifted by a half. And that's kind of obvious just back here from the original definition. Translations act by multiplication by omega. So we're going to change this exponent here by a half comma 1/2. So it's a very simple fact that the soft gravitons shift conformal weights by a half, but it looks very strange from the conformal field theory point of view. Now, in an ordinary conformal field theory, you could never have an identity like this because, there typically aren't continuous spectra of operators. There wouldn't be another operator whose dimension was greater by a half, but there is always such an operator in these celestial conformal field theories. Now, the fact that the correlation functions, the OPEs and the amplitudes are invariant under translations is extremely non-trivial. At conformal invariance, we've written it away so that becomes trivial, but now translation invariance is extremely non-trivial. So let's look at the OPE of two positive helicity gluons. And so we have one of conformal weight H1, another one of conformal weight H2, and these are color indices here. And just by dimensional analysis, the OPE has to take this form up to the leading singularity in the OPE has to take this form up to some unknown function of the conformal weights H1 and H2. Now, these have actually been, this function has been computed in momentum space and can be extracted by doing a melon transform by people who study collinear singularities in gauge theory. But here we're going to see that we can completely determine this function just from the symmetries. So if you take global translation invariance and act on both sides, you shift these weights and you learn that the invariance implies the following recursion relation among the coefficients. Then there's a second symmetry that is this subleading. So there's a soft gluon theorem, and then there's the subleading soft gluon theorem, which is the analog of Lowe's subleading soft photon theorem. And I haven't talked about that, but you can understand that also. I'm not going to write it all out, but that also constrains this OPE coefficient. And so now we have two recursion relations just from symmetry that the OPE coefficient has to obey.
And Andy, I have a trivial question.
Yeah.
These correlation functions, so you have some operators whose correlation functions are going to be holomorphic, if I understand it correctly.
Right.
Right. So we consider a bunch of other operators and you insert this thing and the correlation functions are holomorphic.
Right.
Now, you would like to probably to discuss some condor-intervals of them because the correlation functions are holomorphic.
Right.
On the other hand, the operators themselves have funny dimensions. How is that consistent? So you had this 3/2 and -1/2. How is that consistent?
Okay, so yeah. Okay, so let me give two answers. So that's a very important question. Let me give sort of the practical answer that we've been using, and then there's a more nuanced answer that we don't have in full. This thing here is so the practical answer. So this particular operator here was written down, a long time ago in my 2013 or whatever, and you can just show reverse engineering from the soft graviton theorem that this thing is holomorphic, and so you can take its contour integrals, and it generates, you take the contour integral of this and you get the right, you pick up the pole and it shifts it by 1. Now, the problem is, I think what this thing is actually part of a multiplet, an SL2C bar, a left-moving multiplet. It's annihilated. This thing is annihilated by L bar minus 1. DZ bar is L bar minus 1. But it's not annihilated by L plus 1, L bar plus 1. So if you act on this with L bar plus 1, you get another identity in which there's a Z bar minus W bar on the right-hand side. And in fact, what we think is that this thing oddly lies in a finite dimensional SL2 bar multiplet. And so it's annihilated by L bar minus 1, so you get 0. This operator becomes 0 if you add it by L bar minus 1. You act by L bar plus 1, you get a different operator that has a different OPE relation with a Z bar minus W bar on the right-hand side. And then you act with L bar plus 1 again, and you get 0. And that may sound very strange, but that's related to the fact that the barred weight is negative. And when you, something I wasn't familiar with, but when you have SL2C representations with negative conformal weight, you can have these finite dimensional multiplets. So we think this lies in a finite dimensional SL2 bar multiplet. Z is the unbarred.
So how many components is this multiplet there? In the bar side?
2. This one has 2. It's a doublet. So already in gauge theory, so sorry, Dottie, but you're asking such an interesting question. It's hard for me to restrain.
I apologize.
From giving more details, but I'm a little wary because we're still we're still discussing this. But if we go, we could already ask this in the gluon case. Sorry, you could ask it in the photon case. That's the simplest one. The leading soft photon theorem is an ordinary dimension 1,0 current. The subleading soft photon theorem comes from an operator which is dimension 1/2, a minus 1/2. And there's a current associated with it, which is an SL2 bar doublet. And so it has non-trivial transformation properties. And so to understand how all this is consistent is essentially the project that Alfredo and Mina and Monica and I are working on. And there's a whole algebra of these currents. So it's only the lowest SL2 bar element that has a purely holomorphic OPE. The guy that's one up has a Z bar minus W bar on the right-hand side. Well, you probably don't fully see because I don't fully see, or maybe maybe you saw it after, but yeah. Okay, so anyway, these two recursion relations completely fix these are the two known recursion relations which the Euler beta function obeys. And if we fix the fall off at infinity, then we can just read off what the OPE is. And these had already been computed by Fan, Fotopoulos, and Taylor by direct Melon transform and agreed. We went on to do the general leading OPE for gravity, and we fixed all of them at leading order in 1 over z 1, 2, and it all worked very beautifully. And so we're seeing that these symmetries have some power in telling us something about the theory. Exactly how far, how much we can get, we don't know. Okay, now I'm getting a little bit into what the discussion, the point that Nadi just raised. So here's the OPE. This is just the Euler beta function. And notice if we're going to let this thing, so the standard soft gluon theorem would be where we take H1 to 1, and then we get a gamma of 0 here, and we get a pole. But actually, we get poles at any H. Sorry, any integer H1 or less. So there's a whole sequence of poles. And for every pole, so whenever this k is an integer less than 1, since there's a pole there, we can multiply by, this should be k plus epsilon. So you let the weight approach an integer and multiply by epsilon, and the OPE is still finite because this thing is diverging. So at these special values of the weights, there are special operators that generate the soft symmetries. And the first one is just the soft gluon symmetry. The second one is the subleading soft gluon symmetry. And if we take the lowest bar component of it, as I was saying to Nadi, we get a holomorphic operator, and these obey an algebra. Now, so there's an infinite tower of generalizations of the soft gluon current, the subleading soft gluon current. This also works for gravity, no room on the slide here. And this sheds some light on what various people have been discussing. A lot of people are discussing, well, why aren't there a whole infinite tower of soft theorems? Well, there are an infinite tower of soft theorems to all orders in the expansion in omega, but we're not really getting more information of them, because this algebra has the property that if you know the first two, you can generate the rest. So if you have a correlation function that obeys the ward identity of the first, the leading and the subleading soft theorem, it's automatically going to obey the other ones. Nevertheless, this is a very interesting algebra, and we'd like to understand it. And we feel that this is the language, this is the concise language, the language of asymptotic symmetries, you know, where you're actually writing out the fields and going to null infinity and talking fall-offs and so on. That gets pretty messy, and this seems to be the sharp language in which we can understand what will, and by the way, I'm talking about the symmetries of nature. These are fields that exist in nature, except that gluons are confined, but there's a photon analog of this and a gravity analog of this. And so to find out what all these symmetries are is an interesting problem. Now,
Andy, can I ask a question?
Yeah.
There's in the previous slide, how do you show that the operators are holomorphic? Because holomorphicity means that in the OPE, you've only written out the singular terms. There are presumably non-singular terms which are not holomorphic.
Yeah.
In the OPE written down in the first line.
There are, but they don't have poles.
I see.
And this R is not just O, it's I should have written a K plus epsilon here. So you take this gluon, you take it to the pole, you multiply by epsilon, and all of those will be killed by this explicit epsilon, which is out in front.
I see. So the OPE that you've written, should that be a tilde, or is that actual equality? Or you're saying there are still non-singular terms?
This is a tilde. This is a tilde because this has corrections, but those corrections don't have poles in them.
Yeah, and what about the OPE for R?
Oh, let's see. This is a tilde. Well, I think, yeah, I think this should be an equality. I think it's a tilde because I didn't put the fact, there might be some factors. Yeah,
Oh, okay. Okay.
yeah.
Andy, don't you have poles at half integers? That's one question. And the other question is if both H1 and H2 are half integers, I guess there would be a finite number of poles instead of an infinite.
Wow. Now you've got me worried there's something wrong with my formula. There are no poles at half integers. But this looks like it has a pole at a half integer.
So maybe there's just a typo. You didn't mean 2H.
Well, I didn't type it. I wrote it. But what did I write on the previous? Okay, I'm going to take a pass on that. Nima, do you know what? I don't know. There aren't poles at half integers. I don't know what I did wrong there.
It looks right
Maybe
to me.
that
Your
two
formula.
isn't there. What?
Your formula looks right to me, but yeah,
Maybe it's H1 plus, it's H1 plus H2. Yeah, I'm sorry. I'm not sure. There aren't poles at half integers. There must be something wrong with this formula. I'm sorry.
Once
Okay.
you're at it, the formula with R, so when you said it should be an equal sign, so does it mean that in the correlation function, we can just replace the product on the left-hand side with just a single operator at Z12 without high order terms? Because that's what you answered earlier.
Yeah, that's why there's a tilde. Yeah, this would be, if you compute the commutator, if I turn this into a commutator, right? I haven't said where the right-hand side is.
Right, that would lead to usually to corrections.
Yeah. So that's why that's why there's a tilde there.
No, but I thought
But
because
that actually raises his question again. So the left-hand side, you're at two positions, position number one and position number two. Yeah. And in the right-hand side, you have an ambiguity of where you are. And you can change that at the cost of adding high order terms. But the high order terms are not going to be holomorphic.
No, I think the higher order terms are holomorphic here.
Even though the dimensions of R are non-zero, non-trivial? The way it normally works is the d bar of the operator is 0, follows from a null vector. And then...
Right, there's a null vector here. Indeed, that is exactly...
How can there be a null vector if this thing is a funny dimension? Is it a non-trivial dimension on the bar side?
That's because the weight is negative. That's the interesting thing. If you start with the negative weight and you act with d bar, you'll find that something will become null. It's a 3-line calculation.
What's the conformal weight of this operator R?
the operator R is, let's see, I think its total conformal weight is 1, but it has a high spin.
So even though it's holomorphic, its H bar is not 0 because
Its H bar is not 0. Basically, it comes, right, its H bar is not 0.
So what is its H bar?
In general, its H bar is something like 1 minus k over 2, where k is negative.
Okay.
There's a d bar to the 1 minus k here.
Uh-huh.
And if you hit it with one more, well, you hit it with 1 d bar, it becomes 0. It becomes a null. It's a null state. That's exactly what happens. And it's a cancellation that you can't get when you have positive conformal weights, but when you have negative conformal weights, you can have these surprising finite dimensional multiplets.
Okay.
Is it related to the fact that it's not annihilated by L plus 1? So it's not a high score.
Not annihilated by what?
L plus 1. I
It's certainly not annihilated by L plus 1. It's in a multiplet whose dimension is well, we could talk about low values of k, right? So for low value, so k equals 1, everything is fine. It's just this, with k equals 1, we get 1, 1, and we get 1 here. This is just the OPE of the soft gluon current. But already at k equals 0, we're talking now about the OPE of the subleading soft gluon current. And then everything is in a doublet. And I haven't written out, we have in our notes, but it's not fully debugged. We could write out the OPE for the whole multiplet. And then you know, you get a doublet. So what happens here is you take the OPE of the leading soft gluon, the subleading soft gluon. The leading one is a singlet. This subleading one is a doublet. You get a doublet on the right-hand side. Now you take a doublet with a doublet, you get a triplet, right? So if you take k equals 0 with k equals 0, you get k equals minus 1. So you have to make a triplet out of 2 doublets. So there's an algebra there, which, you know, we haven't fully debugged.
I think Nati meant to ask that in ordinary unitary CFT, if an operator is holomorphic, then its H bar vanishes using the commutation relation between L bars. But here, presumably, some of the assumptions we usually make doesn't.
Yeah, exactly. So there's some very weird things that happen. So these integer negative conformal weights are very interesting. So already you could do it yourself in 2 seconds if you take something with weight minus a half, then and you act on it twice with d bar. If you assume you have a state that's annihilated by L1 and it has L naught on it is minus a half, just 2 lines of algebra, you'll find that L minus 1 squared on it vanishes. Is a null state, gives a null state. Yeah, so we were really surprised, surprised by this. It's such an elementary calculation, but one that you wouldn't do because you don't usually think about things with negative weights. But in QED, these negative weight things are important. They generate the subleading soft photon theorem. And in gravity, they generate the super translations. So we need to understand their properties. Okay, so now
properties. Sorry, one question: are these properties you're discussing true for tree-level amplitudes or to all orders, or for the exact amplitudes?
So here, it depends what theory you're talking about. Here, you know, probably in n equals 4, and indeed, I think people have proven these versions of these things in n equals 4. It might be true for the planar diagrams or something. But in the gravity case, you know, it's a little different for everything. In the gauge theory case, if we're talking about the real world, you know, gauge theory confines, and at long distances, we don't have any of these currents. But it's still, you know, an interesting model. In the gravity case, I think that certainly the leading leading one, which is already an example of one with negative dimension, is exact. That comes from the leading soft graviton theorem. The subleading one, probably also an exact property of the theory. And then the subleading one, I don't know. Again, now in QED, I imagine the subleading one in gravity is kind of like the subleading one in QED. In QED, you have the leading one, of course, is exact. That's the soft photon theorem. And the subleading one, there's a small list of finite dimensional operators that can correct it. And those corrections are very interesting. There's still a theorem, but it's corrected. And in fact, we had to use those corrections. That correction is already there in tree-level Einstein-Yang-Mills theory. The subleading, because there's a coupling between a graviton and two photons, and the subleading soft symmetry actually, surprisingly, turns photons into gravitons. And we had to use that term when we computed the OPEs. I went through that rather quickly, but that term has an important consequence. So as far as what's been proven, you know, it's been proven that the leading graviton and photon ones are exact. The subleading ones have some limited form of corrections which can be controlled. And beyond that, I'm not sure what the status of them is going to be.
Okay, thank you.
Okay, now, so I've talked about 2 points, 3 points, now I'm on to 4 points. And oh my God. What am I going to do here? I've already gone for an hour. Let's see. View full screen.
Slowed you down, so we'll give you more time.
Okay, I'll try to speed up a little bit though. And okay, so 4-point scattering. So the simplest case of 4-point scattering is 2 massless scalars with a massive scalar exchange. You can compute the melon transform. And one of the interesting features is, so the what we would call T over S in space-time language turns out to be precisely minus the conformal cross ratio on the celestial sphere. And you get a delta function, which says that all 4 points have to lie on the equator. And that's kind of funny, but I'm going to have more to say about it on the next slide. But now we'd expect that this would have some sum representations as a sum over conformal blocks of OPE squared times the conformal blocks. And the fact that it should have this kind of representation is already reminiscent of string theory. I mean, string theory, you could have either T channel or S channel, but you don't need to add them. And now we're saying that that statement follows basically just from, in some modified form, or a related statement follows from conformal invariance. So we've dove into the details of the conformal block expansion of this simplest of 4-point amplitudes. And some beautiful things happen. Let me just make a couple of points about the answer. The first thing is we found that it factorized on 2 different kinds of states. One are, you had the standard conformal blocks and the OPEs, which Shuhong and Lam computed a few years ago. They computed these OPEs, and the conformal block expansion gives you those OPEs times the conformal blocks with the weights lying on the integer real axis. Then we got this other thing which really bothered me at first, which looks like propagating in the intermediate channel were states, these weren't conformal blocks. And then one of my students says, hey, this is the conformal block of a light ray transform. And I'm like, why are we seeing light ray transforms here? So it turns out that in 2-2 signature and even 3-1 signature, there are other solutions other than what Sabrina and Shuhong wrote down. There are solutions, you just can write down the solutions of the wave equations where H is not equal to H bar, where H is equal to 1 minus H bar. And they're perfectly good solutions of the wave equation, and they perform an alternate basis. And in the conformal block decomposition of the 4-point function, they appear. Another beautiful thing that we see is, of course, each one of these conformal blocks doesn't have any delta function singularity in Z, but amazingly, when you do this, the sum over all the intermediate states in the conformal block expansion, it generates the delta function. And the fact that you have a sum was, of course, forced by translation invariance. Translation invariance related things of different conformal weight. So translation invariance imposes the fact that there should be an infinite number of fields transforming in the intermediate channel, and that these must sum up to a delta function. So usually in conformal field theory, you would say you don't get singularities at finite points, but their infinities can come from other places. And in this case, we see exactly where their infinities are coming from. It's coming from the sum over the infinite number of primaries, which is implied by the translation invariance of the theory. Now, there's a more complicated formula. I took the contact limit, where it's just a 4-point contact thing here. There's a more complicated formula, which can also be decomposed, of the finite M thing. But an interesting thing here is that you can only think about the contact limit as the limit of the thing with a massive exchange, because the melon transform of the contact interaction doesn't quite converge. And so this conformal block decomposition of the contact thing sort of resolves this contact 4-point function and tells us that we must have some kind of intermediate states. It is looking very stringy. You know, you need intermediate stuff to smooth this out.
Andy, I don't understand this delta function. Is it covariant under the conformal group?
Oh yeah, of course everything is covariant.
But it's z minus z bar. So if I shift z by something, then it will not be.
No, it's the cross ratio. It's the conformally invariant cross ratio.
So z is not a coordinate on it.
Z is Z13, Z24 over Z12, Z34.
I see.
It's just a standard cross ratio. The thing, it's T over S, sort of the Reggie parameter in space-time becomes the now, importantly, there's another factor, a prefactor, a ubiquitous 1 over sine pi beta that is not factorizing properly. We don't know what that means. So I don't know. We're confused about that factor. So I'm not going to say anything more because it'll probably be wrong.
Could you say what beta is?
Ah, sorry, Jesus. Did I not say what beta is? Okay. Beta is the sum of the, did I write it there? I can't see that on my, yeah, beta is the sum of the external conformal weights minus 4. Delta 1 plus delta 2 plus delta 3 plus delta 4 minus 4. And it is very strange that in an ordinary conformal field theory, the 4-point amplitude depends on all 4 conformal weights individually. It's very strange that it depends only on beta, only on their sum. And this was shown some time ago to be, it's not that hard to show, but there were a couple of papers showing that in fact, the whole thing can be a function only of beta. And indeed, we're only allowed to have, since we start with a space-time amplitude that depends only on S and T, we can only, and it can only, the celestial one can only depend on 2 things, and that would be the sum of the conformal weights beta and the conformal cross ratio Z. So it seems crazy that any set of correlation function with good properties would satisfy all this, but okay, here they are. All right, so this is getting into this paper now with soon to appear with Nima and Monica and Anna. And so I want to stress a little more the sort of anti-Wilsonian nature of this. So we're throwing out the old idea that you organize all of physics in terms of length scales. And of course, there have been little hints of this in string theory with the UVIR connection, and lots of people have been saying things like this from different points of view, that maybe as compelling as Wilson's picture of the world was, maybe there isn't, there's other ways to think about things. And here we're scattering things in which we integrate overall energies. So we've completely thrown out the whole Wilsonian picture. So what do we see? Well, still we see, interestingly, that sort of the lessons from the Wilsonian story are reflected in a very beautiful way in the analytic structure of the scattering amplitudes. So let's talk now about this 4-point, but in much more general terms than those very concrete formula we were writing before. So we're going to start out by assuming that, as people like to in quantum gravity, that the amplitudes are all very soft at high energy. And indeed, we expect that due to black holes, that this goes like e to the minus s, because, you know, we can't, the amplitudes, exclusive amplitudes have to be very soft because we have to sum up infinitely, a black hole's entropy's worth of them in order to get something finite. That's an argument that's been discussed elsewhere. Let me not go over it. Then, but let's expand this at low energies in terms of the center of mass energy S. And usually you write APQ, T to the Q, but here we want to write it in terms of the cross ratio Z. So we have these function AP of Z, and these are the coefficients or resummed coefficients of the EFT hedron, and they have very interesting positivity properties. And now we take a melon transform to get the melon amplitude, which after some collapsing of delta functions and so on boils down just to this. And since this is soft at high energies, we're never going to get a divergence at large S. The only place where we can get divergences at tree level, this is tree level I'm talking about now, but most of the story carries over to loop level, is at near S equals 0. And we know exactly how those will go. We'll get a factor of S to the P here plus beta minus 1. So we'll get things that go like AP of Z, beta plus 2P. So what the 4-point and similar statements for higher point amplitudes look like is that they are meromorphic. We're integrating over all energies. They're meromorphic. The only source of divergences are infrared poles. And the residues of those poles are just the terms, the coefficients in the effective action. And now, if we look at this previous slide, we have poles here at all integer betas. Particularly here, we have integer betas. And but we can't, when we embed this in quantum gravity, those poles have to disappear. The 4 massless scalar amplitude can't have poles at positive beta if we have this exponential softness. Those are related to UV divergences. And so all those poles at positive beta get erased in full quantum gravity. So the picture is that the 4-point amplitude is, analytic structure is that it has poles only at negative even integers. Now, what happens when we go to the quantum theory? Well, the UV behavior, and here I had to use smaller font to get it all on the page. So, okay, the UV behavior, still soft. Indeed, the black hole argument is really a quantum argument. So we still expect divergences in the celestial amplitudes from the IR, and it's still meromorphic. Now it turns out that now we'll get logs, and the logs will turn some of the poles, the simple poles in the tree theory, to multiple poles in the quantum theory, higher order poles in the quantum theory. We also get IR divergence from exchanges of soft particles in exclusive amplitudes, but these are very well controlled. So we need an infrared regulator to define it. These are very well controlled by the soft theorems. And we can write down explicitly how they look. They look like this. And so now if we take, this is in momentum space. Now if we take the melon transform of this, we find that the melon transform factorizes in a very simple way. And the cusp anomalous dimension, which characterize the infrared divergences, appears, it shifts the conformal dimension of the charged states. And after you perform that shift, all the divergences in the hard part of the scattering amplitude are gone, but it's multiplied by a soft scattering amplitude, his form takes the form of a correlator of exponentials of free bosons. And in fact, this correlator seen before, it's the correlator of the Goldstone bosons of the spontaneously broken symmetry of supertranslation invariance. And these hard amplitudes, we further showed, are nothing but the infrared safe scattering amplitudes that you get if you do a Fadeev-Kulish dressing of the states. Now, one of the disturbing things about the Fadeev-Kulish formalism is that when you dress, so they dressed charged states with clouds of soft photons to cancel infrared divergences, but that involved an arbitrary form factor that depended on the momentum. So there was an ambiguity that there was no natural way to fix. It had to have a soft pole, so you can't make it a momentum eigenstate, but you can make it a conformal eigenstate, and that gives you a unique and natural basis. And indeed, that's exactly the one that is appearing here. And so there appears to be an infrared safe hard S matrix for in QED, and the same thing works with some modifications in gravity. Okay, let me close with a question. I think one interesting problem is to find the most general form of the 4-graviton amplitude and consistent with conformal invariance, crossing symmetry, supertranslation symmetry, 2D crossing, 4D crossing, causality. There are a bunch of constraints in this TAIFR paper, and it really is, like a rabbit that's being chased into a hole with no exit. We seem to be getting more and more constraints on what form this can take. And I think that's a very interesting problem that we might actually hope to solve. So in conclusion, the reformulation of Minkowski scattering as correlators on the celestial sphere is leading to new insights, and there's a lot to understand. And thank you for listening.